Thank you, Peter, and thank you all the organizers for inviting me here. I'm just thrilled to be here, I have to say. So my title in the program, it had two more phrases. It said universality and anomalous temporal decay. I promise I will play those songs as well, okay? All right, so this is greatly joint work with Peter. I'm going to start with overview of what we have found in the past 4 or 5 years for the focusing analysis equation. And I will also mention some ongoing work with Elliott, Blackstone, Robbie Buckingham, Thierry Laurens, who is here, Liming Ling, and Giorgio Young. And I will also talk about what's next in the pipeline. And that stuff really culminated from the discussions we had with Roland Killip and Monica Vishan when I was visiting them, so thank you. Anyway, so I'll start with the focusing nonlinear Schrödinger equation, which what the talk is going to be about, well, almost a good chunk of it, okay? It's an integrable nonlinear wave model also that arises in certain asymptotic reductions of other physical systems, like the small amplitude water waves here. It admits solid-on solutions, breather solutions, okay? And also solutions that are localized in space-time that are interesting. Those are thought to model rogue waves, okay? But the simple such space-time localized solution, I'm going to refer to them as rogue wave solution. I'm not making a claim about water waves here, okay? It's just localized in space-time, all right? So the simplest one of them is due to Peregrine, which I denote by psi1. So this is a rational relative perturbation of the background solution e to the it of this equation. And the perturbation is localized in space-time. You see as xt goes to infinity, it goes to 0. And at t equals 0 and x equals 0, it forms its peak. The peak amplitude is 3. It's an exact solution. And the background amplitude is 1. Okay, so the peak amplitude is 3 times the background amplitude. Okay. This equation, okay, it comes, because it's integrable, it comes with a nonlinear superposition principle. And this allows one to actually construct these exact solutions from scratch, or also maybe somebody gives you a background field and you want to nonlinearly superimpose on top of that such coherent structures like solitons or breathers, okay? So we are speaking of the Backlund transformations induced by Darboux transformations here when we say nonlinear superposition principle. And I'll give a quick overview of what a Darboux transformation is really, okay? Okay, without mentioning too much about integrability, maybe, but there are 2x2 matrices, capital X and T, that are matrix polynomials of a spectral variable lambda, all right? X is a linear polynomial and T is a quadratic polynomial of lambda. And the coefficients of those lambda terms depend on psi of xt and its x derivative, okay, as a function of x and t, such that this condition, also known as the zero curvature condition, holds for all lambda if and only if psi that appears in the coefficients solves the focusing analysis equation. But this immediately tells you that, oh, okay, if you look at this overdetermined system of linear, first-order linear ODEs, okay, where x and t are the coefficient matrices and require that they are simultaneously solvable, that compatibility condition is exactly this condition, which is equivalent to the analysis equation. So it tells you that focusing analysis equation arises as the compatibility condition of this system. Okay, and here V is just some auxiliary vector, okay? Just a vector unknown. All right, so what's a Darboux transformation? Well, it's essentially just a gauge transformation. You multiply the solution of this equation that you pick by some matrix G that depends on xt parametrically, but also depends on lambda, and define a new vector V1, all right? So that there's an implied system V1 x derivative equals some coefficient matrix times V1, and there's also the time ODE. So the Darboux transformation ensures that this system of equations is exactly the same form as this system. What do I mean by that? Well, the only thing that's different is that this psi function is replaced by psi 1. Okay? Everywhere it's just, you just take it out and put psi 1. Okay? But because of this equivalence, now psi 1 is a solution of nonlinear Schrödinger equation. Okay? So how do you build this G? Well, it's built out of really, you take this some solution V of this system, and you evaluate it at some point of your choice in the lambda plane. Okay? That's a specific choice of a vector solution. It's a function of x and t. That's how you build G. Okay? And of course, now there's an induced transformation on psi that gets mapped to psi 1. That's the Backlund transformation that goes back to 1880s, to the work of Backlund and Bianchi in the context of sine-Gordon equation. There are parameters here. Choice of lambda 1 in the complex plane is a parameter. Okay, it's an internal parameter that's hidden inside this psi 1. And also, you want to choose this V maybe from a fundamental solution matrix. That means you're taking a linear combination of the columns. Okay, that means you have two complex numbers to pick, right? So those are also internal parameters. Okay. All right, so one may take the background solution, Q equals e to the ID as the seed, okay, for this Darboux transformation. And it turns out that if you apply this transformation repeatedly, where you pick this special point lambda at each iteration k to be I, then at each step you preserve this space-time localization of the new solution. Okay? So it decays to the background field e to the it as xt goes to infinity in any direction. Okay, so the resulting object is called a higher order Rho wave. And it can be written in terms of determinants by some Kramer's rule, okay? And the dimension of the determinant grows proportionally to the number of iterations you make, and that's called the order of the solution, okay? And as I said, new parameters in principle can enter the solution at every iteration, okay? Lambda 1 is fixed, but there are these C1, C2s that enter at every iteration to the solution. Okay, so when it's said like this repeatedly, I mean, it reads like a trivial thing, but this is not straightforward at all, actually, because when you build this Darboux transformation, the first application of it to V, okay, it introduces a singularity at lambda 1. So if you want to evaluate V1 at lambda 1, you have a problem, okay? So there are ways to overcome it algebraically. Okay, sometimes you insert it at a nearby point or take a limit, etc. But also there is now a framework to do it in the context of a modified inverse scattering transform. So it's just complex analysis associated with this Lax equation. Okay, so that's something we figured out in this paper with Peter. All right, so here are some plots. Okay, so if you choose C1 over C2 to be plus or minus 1, it turns out, as they say, you get the most bang for your buck, meaning that the solution is highly symmetrized and it produces a massive peak in the center. Okay, so this is the Peregrine solution. That's the second order Rho wave. These are called fundamental Rho waves, okay, of order k. This is the order 2. I plotted the modulus, but the scales are different. Okay, this goes up to 5. The height is 5 actually, the peak height, and here the peak height is 3. All right, actually, we know since last 13 years that, okay, for these symmetrized solutions, you know the peak amplitude. It's known to be 2k plus 1. So it grows linearly with k. And here's a plot of these first 4 solutions, all on the same scale. You see that the amplitude grows, okay, with k, as the formula tells us, but also the wave patterns around the peak become more complex. Okay, and there's a density plot of the amplitude of the 8th order solution. When you look at it, well, okay, there's something interesting here. Clearly, there's an hourglass-shaped region in which there's something different happening compared to the outside, okay? So you want to understand maybe how do these wave patterns look like as the amplitude or the order becomes large, okay? So if you want to study, okay, the wave patterns generated by Rho wave solutions with extreme amplitude, say, one can leverage the following fact. If you increase the order, you derive the amplitude to be large. So maybe there's a way to work in the large order regime asymptotically. Okay? Treat k as an asymptotic parameter and send it to infinity and try to get some information about psi, okay, as a function of xt. Of course, if you want to send k to infinity in k by k determinants, that's not so convenient, I should say, okay. But in this paper, we put all of this into a 2x2 Riemann-Hilbert problem framework where k just appears as an explicit parameter. It's just the power of some matrix, okay. So that gave rise to, that made this large order limit, k goes to infinity, tractable analytically, okay. And that's what I called extreme superposition, okay. So that's the first buzzword in the title, okay. Sending k to infinity because you are nonlinearly superimposing a lot of these coherent structures on top of each other, okay. Infinitely many of them. Okay, so the first result is this, which we call the near field limit. So one takes these family of solutions and one zooms in as the order becomes large, the amplitude is becoming huge, okay? One zooms into the focal point at this rate. So here capital X and T are some rescaled coordinates. So you pick capital X and T in a compact set, all right? And then you zoom in at an origin in this parabolic rate, okay? And you also rescale the amplitude, okay? This limit exists. And it exists, okay, there's a function that depends on capital X and T that's equal to that limit. Not only that it exists, it also is a well-defined solution of the focusing analysis equation in the capital XT coordinates, okay, the rescaled coordinates. So you zoom into the peak and you look at this in this new coordinates, that thing also solves the same equation, okay? The limiting profile solves the same equation. And because it's an infinite order limit, we called it the Rho wave of infinite order, okay? So that's the second buzzword in the title. Okay, so then I, of course, went online and just put that phrase in. This is what the internet thinks about it. This is a generative model, okay? I don't know which one, but I just told them to produce a Rho wave of infinite order picture for me. I had to say it captured the Japanese anime flavor, but a more accurate picture is coming, okay? All right. All right, so, okay, next, universality, okay. So this IST idea where, you know, we can encode iterated applications of the Darboux transformation within some IST-based Riemann-Hilbert problem framework, okay, of course, doesn't only apply to Rho waves. It was cool to do it for Rho waves because there wasn't an IST that captured them by the time when we wrote the paper. But actually, one can just take the zero background instead of e to the it, and pick some xi in the complex plane, in the upper half plane, okay, and just apply an iterated Darboux transformation with these, okay, with these choices. And now the resulting solution, which I'm going to denote by qk, is a multi-soliton, but it's not a multi-soliton in the sense that you have, say, k simple eigenvalues without a reflection coefficient. Actually, you have just a single point, an eigenvalue at a single point xi with algebraic multiplicity k, okay? All right, of this differential operator here. Okay, so here's how those solutions look like, all right? Very different than these guys, okay? These are the Rho waves, this is the multisoliton of order k. So with Robbie Buckingham, we showed that the same infinite order solution also shows up as you zoom in exactly in the same scaling to the focal point of these family of solitons as you send order to infinity, okay? All right, so here's also a, what is it called, surface plot of these solutions, just to show everybody, okay? So I'm not sure how visible it is. It's not good from here, but okay, so this goes up to 35, all right? So this looks tiny, but actually the peak is 16 here, and it's sitting on a zero background. Okay, so it's a huge peak, and this is a 16th order solution. There's a really narrow peak here. You can see it goes all the way up to 32. Okay, some exact solutions. All right, but they produce the same limiting profile. Okay, and in this transformation, when we were writing that paper, it turns out that, okay, you can actually, you don't care about the fundamental nature of these soliton solutions maybe, so you can allow yourself to pick some different C1 and C2 in your Darboux transformation, but stick to the same ones in the iteration. So you pick them once and for all, and you always choose the same linear combination, okay, in your iterates, okay? So that means the limiting object for the solitons depended also on two complex number parameters. So it generalizes our first observation with Peter and Liming-Link. So we call those solutions to be general Rogue waves of infinite order because of this C1 and C2. I wrote it in this projective plane notation only because at the end of the day, you can prove that the solution only depends on the ratio of C1 and C2. Although its representation, if you just take it at its face value, it depends on C1 and C2, okay? And if C1, C2 is equal to 1, you get the good old first result. Okay, so here are some plots of the solitons, okay? So this is unscaled. I'm just showing you that, okay, as k increases, you see that the peak increases and these guys really look different. This is a choice. C1 equals, I can't see it. C1 equals 1 and C1 equals 1 over 4. C2 is 1. So it's skewed towards right a little bit. It's not in the center, okay? But here are the rescaled potentials. I said t equals 0, and I rescaled x and rescaled the amplitude. So after the green 8 order one, I don't think the eye can tell the separate curves, okay? So they seem to converge pretty rapidly empirically, okay? And so far, this is all pointwise or, you know, uniform convergence on compact sets topology. All right, so if we go back to these two solutions, this is the rogue wave solution of order 8, this is the multi-soliton of order 8, you look at them and you see that, the boundary conditions satisfied by these solutions are pretty different, actually. This goes to e to the it, okay, provably, as xt goes to infinity, all right? So it looks like this constant amplitude background. This doesn't go to anything, okay? It has these information propagating, okay, all along. So, but in the near field large order limit, they both look the same, okay? So we asked, maybe there's more to it, okay? And actually there's more. So in this paper, what we proved is that you can take virtually arbitrary background field. It doesn't need to be an exact solution. It doesn't need to be satisfying certain boundary conditions, okay, for which the inverse scattering transform applies. No, it doesn't matter, okay? What you can do is you can start with a Riemann-Hilbert problem, like a blank canvas, and you can prescribe some jump conditions. As long as you impose required Hölder continuity assumptions on these jump matrices in the Riemann-Hilbert problem, actually you can take the same limit, and you show that, the general rogue waves of infinite order appear if you just iterate infinitely many times this Darboux transformation on this arbitrary background. The background can be, for example, some type of a soliton gas, right? So because the soliton gases are supported with arcs, some densities on arcs, right? And if the densities vanish at the endpoints, that means the jump matrix tends to the identity, and you can complete it to a loop, okay? And then, okay, how do you prove that? Okay, so the proof, actually the entire paper is the proof.
If I can interrupt, so when you say multiple Darboux transformation,
Yeah.
you mean taking the same point?
Same point. That's what I mean by iteration. Yeah, that's what I mean by iteration. It will be interesting to jump around, but okay, that's a separate story. And the way to prove it is that is you map it to a compact contour, okay, because you can by your assumptions. And it boils down to really controlling, I think, the Hölder operator norm of inverses of two singular integral equations as xt goes to the focal point and the number of iterates goes to infinity at the same time, okay? So that's how you prove that result. All right, so what does this tell us? Well, in a sense, okay, it might be a broad claim, but in a sense, all this rogue wave type formulations where there's a huge peak forming, okay, in the NLS equation, governed by the focusing NLS, having sufficiently large amplitude look the same near their focal point. You always see the same structure, okay? All right, so there's another context where the solution appears, okay? And the idea really goes back to 60s, Talanov's work. So there's this thing called initial profile called self-focusing Talanov pulse, okay, for the dispersionless NLS system. So you see the amplitude blow up, referred to as collapse in finite time. And there's this paper by Süleymanov where Süleymanov took this parabolic profile and formally studied what happens if a small but non-zero dispersion is restored, okay? And then the scaling argument shows that the same solution actually, with C1 equals C2 equals 1, okay, emerges in the small dispersion limit to describe this self-focusing dynamics, okay? So that paper came out before ours. And a particular type of Talanov profiles actually can be approximated by semi-classical solitone ensembles arbitrarily well. And this is ongoing work of Robbie Buckingham, Bob Jenkins, and Peter Miller. And there you can prove actually rigorously that this type of focusing in the semi-classical limit is governed by the Rho wave of infinite order, okay, this solution. And what's the mechanism? The mechanism is accumulation of eigenvalues, okay? Simple eigenvalues at a point, all right? So in the previous examples, what I showed was accumulation of eigenvalues of multiple order to infinite order, okay? Of algebraic multiplicity high to infinite order algebraic multiplicity, if you will. Here, now it is simple eigenvalues that come together, okay, when you take this limit. So I'll say a little more about this. So what makes the structure appear, okay? So here are some observations. All of these limits that I described producing these infinite order solutions are essentially large amplitude asymptotic regimes, okay? So that seems to be a feature, okay? And another common feature is that, well, as the amplitude is exploding, simultaneously, the support of the solution is collapsing. So the wave profile near the peak is getting narrower and narrower as it becomes taller, okay? So you see that kind of behavior. But of course, I mean, you can take any localized solution of the focusing NLS equation, call it psi, and then you can just generate a family by the scaling invariance, right? Okay? So as k goes to infinity, of course, it exhibits explosion and collapse, but without producing anything new. There is no change of profile. So it seems like one absolutely needs some kind of accumulation of singularities in the scattering side or the complex plane, or accumulation of eigenvalues for the Zakharov-Shabat problem. Okay? That seems to be the essential feature. Okay, so I'm going to give a mathematical definition now of this special solution of the focusing NLS equation, and I'm going to talk about its properties. So what is it? Well, the solution can be defined, actually, I think this is a really convenient definition. It can be defined in terms of a Riemann-Hilbert problem, okay? I tried to minimize the amount of Riemann-Hilbert problems in the talk, so I think we have only one, okay, and that's it. So what do we do? Okay, these are the C1 and C2s that I've been mentioning. You construct this matrix G, okay? It looks like a really specific matrix, but actually it is the most general matrix that satisfies these conditions, okay? It's unimodular and it has this Schwartz-type reflection symmetry. And here, star means pointwise conjugate, not the Hermitian. And sigma 2 is the second Pauli matrix. Okay, so we pick some C1 and C2, and let xt, capital XT, to be arbitrary. And the job, if we accept, is to find some function of 2 by 2 matrix valued function of lambda that's analytic of the unit circle. Actually, any Jordan curve that encloses the origin would do. Okay, there's nothing special about the unit circle. Okay, so it's analytic. And its boundary values exist, okay, from either sides, plus from outside, minus from inside. And these boundary values are related by a jump condition that's multiplicative. That's given by this. P plus is equal to P minus times okay, e to the, so this exponential raised to power sigma 3, so it's a diagonal matrix, conjugating this parameter matrix G. Okay? And you say, okay, at infinity, P is identity. Okay? So, okay, so these are the conditions that constitute a Riemann-Hilbert problem. And it's not immediate that this Riemann-Hilbert problem has a solution. We burned our bridges. What do I mean by that? Well, okay, there are discussions about the initial value problems in the morning. So this doesn't come from an inverse scattering transform in the sense that, okay, somebody handed me a nice initial data potential. I computed the scattering data, real solutions, et cetera, and I wrote down a Riemann-Hilbert problem to encode the inverse scattering transform. No, it arises from a limit. Okay, so there's no reason a priori for it to have a solution at all. Okay, on the face of it. But it does have a solution because you have a vanishing lemma that you can use. It's in the work of Shinzhou. And actually you get more properties out of it. The uniqueness is easy. Existence was an issue, okay? So there's a unique solution of this Riemann-Hilbert problem, and actually that solution depends in a real analytic sense to capital X and T, and also the real and imaginary parts, those real numbers of C1 and C2. Okay, that are in the elements. Okay, and then from that unique solution, remember, P goes to identity. So I read its off-diagonal term multiplied by lambda. The off-diagonal goes to 0, obviously, not when I multiply it by lambda. So I read that residue at infinity multiplied by 2i. That's the definition of general Rogues of infinite order. And that function of xt solves the focusing nonlinear Schrödinger equation in capital XT variables. And here C1 and C2 are just parameters, so it's a family of solutions of the NLS equation. Right, so, okay, so this seems to be a universal object that appeared in at least 2 different settings, right? Actually, there are other settings that I didn't mention, unfortunately. But so one should understand its properties, okay? So how can we understand it? Well, okay, what are the exact properties? Symmetry, special values, maybe other differential equations satisfied by this solution. Okay, that's one avenue. Okay, then one can also try to understand its asymptotic properties. Okay, what happens if x or t becomes large? Okay, can we describe the solution? Can we draw a picture of it, right? Or one can try to actually compute the solution accurately in the xt plane by some numerical method, especially for intermediate values of x and t where the second point fails, okay, if you have it, right? So in this preprint, we did all of these 3 to sort of like have a holistic story about this solution family. Okay, and in the special case when C1, C2 are 1, several of these properties were proven by us, and some were also noted independently by Suleimanov in his paper. Okay, I'm going to start with exact properties here. So, all right, first, I already said that it's a global solution of the focusing NLS equation. How about regularity? Okay, it depends real analytically on x and t, okay? All right, so that's the theorem. And there are some other symmetries that are easier to prove. You get all of these out of the Riemann-Hilbert problem, all these properties. So what are other properties? Well, it's not an even function unless C1 and C2 are equal. However, if you reflect with respect to x, you stay in the family, okay? All right? And there's the time reversal complex conjugate symmetry almost, okay? But you need to also conjugate C1 and C2, all right? There's an interesting degeneration property that gave rise to another working draft right now. If you take C1 or C2 to be 0, you get identically the 0 solution because you can solve the Riemann-Hilbert problem directly, analytically, and the solution is a diagonal matrix, so its 1-2 element is 0, okay? That's where it comes from. And actually, it turns out that that Riemann-Hilbert problem can also be solved analytically when x and t is equal to 0, from which you can recover the values of the solution at the origin and its first derivative in x. All right, so these are some exact properties that are relatively easy to get. Some other exact properties that are not so straightforward, I would say, to get. So this solution has an interesting property in the following sense. If you freeze T, it solves ordinary differential equations in X, more or less, and vice versa. Okay. All right. So, so here's the first one. If we set T equals 0, capital T, and substitute capital X is -1/8 little x squared, and multiply by x squared, take a log, take a derivative, take the reciprocal, okay, and define this u of little x, right? That is a solution of the Painlev 3d6 equation, where these formal monodromy parameters are taken to be 0. Right? It's a solution of this differential equation. And it's an odd function of x, analytic at the origin, and it has a Taylor expansion. Of course, it looks like this. So the first term is 1 here, and you can also compute the third derivative. Exactly this, yes, but next slide, no. Okay, so if t is not equal to 0, you go to the second equation in the hierarchy of Saka. There's a hierarchy of Painlev 3 equations. So the moment t equals 0 kills a bunch of like fourth order terms in the differential equation. And if you just don't kill them, okay, you can still show that, okay, it's a type of Painlev 3 equation. But it's the second equation in this hierarchy. And it remains in that family for all t. Okay, so t equals 0 is a special case. Okay, for x fixed, this also satisfies ordinary differential equations in t. They appear to be an integrable system. It has its own lax pair with respect to lambda and t. Okay, that's how you prove all these things. Okay, but we weren't able to identify it for general x. However, when capital X is 0, if one writes capital T equals little t squared and defines this function here of little t, t is real here, okay? And you also want to pick C1 and C2 to be the same. Then it turns out to satisfy Painlev 3d7 equation in this form, where these curly AB parameters are just 1/2i and 4 epsilon, and epsilon is just a sign. Okay. And this also has a Taylor expansion at the origin, and u prime at 0 is 4i epsilon. Okay, now asymptotic properties. So these are the exact properties of the solution. Interestingly, it solves ordinary differential equations with respect to both of the independent variables. And not only that, it solves some ordinary differential equations, you can identify them, right? Okay, so asymptotic properties before, so asymptotic properties, so how does this work? Well, okay, so if you look at the jump matrix for this solution, for this Riemann-Hilbert problem, you see that, okay, the lambda dependence, which is the independent variable of the Riemann-Hilbert problem, comes in as an exponent, okay? It depends on lambda through exponentials. And those exponentials depend on x and t in a singular way as you send xt to infinity. So this looks a lot like a contour integration scenario, right? And you might think of things like, okay, asymptotic methods like steepest descent method. So, of course, solving a Riemann-Hilbert problem is not at all evaluating some contour integral, all right? But there's a very similar but rigorous, okay, very powerful technique due to Persuadevt and Shinzhou that came out in this paper. It goes by the name non-commutative steepest descent method because you're dealing with matrices, okay, instead of scalars, all right? Or sometimes it's also referred to as nonlinear steepest descent method because it applies to nonlinear integrable equations, okay? But before giving you some asymptotic information, this also provides a way to compute these solutions, okay? Remember, all we have is a Riemann-Hilbert problem, all right? There's no initial data, there's no formula, so there's nothing to do time stepping on, all right? Well, one can probably do the following, take the ODE and start at 0, where you know the solution, and try to create an X profile. But as you will see that the decay in X is so slow that I don't think it's going to work. So the way to compute this solution is to solve the Riemann-Hilbert problem numerically. Okay, so I'll just give a quick overview of how that works. It goes back to the paper of Xi and Olver in 2012 for Painlev 2, and there's a great book. I mean, there has been produced a lot by Tom Trogdon, Bernard Olver, Bernard de Koninck, Sheehan Olver since 2012, okay, on numerical solution of Riemann-Hilbert problems, and most of it is collected in this book. So the idea is this. The steepest descent method involves deforming contours so that oscillatory or large jump matrices turn out to be small, okay? Or the jump matrix is not small, but close to the identity, away from some isolated points maybe, and you collect the contributions from these isolated points, which you can solve the problem almost exactly around those points, okay? So that's in a nutshell how the method works. So once you get into a Riemann-Hilbert problem, which is asymptotically under good control as x or t are going to infinity, okay? It is a jump condition that looks like this essentially, okay? M plus equals M minus on some contour that's defined, it's no longer the circle, okay? And M tends to the identity matrix as lambda goes to infinity. So that's more or less your starting point for numerics. And then you can write down this ansatz, as you can write M as identity plus the Cauchy transform of some unknown density. And you pick a suitable basis depending on the behavior of M at possible endpoints of your jump contour, okay? And then this results in a singular integral equation that you can solve by collocation, okay? And most of these detailed and complicated parts of collocation, choice of basis, etc., are handled by Tom Trogdon's operator approximation package for Julia, okay? In somewhat a black box fashion, right? Okay, so here's the more accurate picture I was promising, okay? I think it looks much better than the artificial intelligence picture. Okay, so the good thing about it is that the Riemann-Hilbert problem you are solving depends on xt. If I go back one slide, 2 slides, 3 slides, okay, it depends on xt parametrically, like an inverse Fourier transformation integral, right? So you give me your favorite xt values, I just plug them in, and I solve a lambda problem. So that means I can fire up the supercomputer, send a dense grid of xt values, and tell them to go at the same time. And you can compute these solutions relatively fast in that way, okay? So this is the solution when C1 and C2 is equal to 1. So you see like there's a peak that's of height 4, all right? And the solution seems to be localized on a 0 background, okay? All right, so here is when C1 is 1/2 and C2 is 1. So it shifted a little bit right, okay, leaned towards right. So this region has become quieter compared to this region. And that continues, okay? We have an explanation of this phenomenon coming up, but not in this talk, okay? As C1 goes to 0, for example. All right, so, and this is a software package now that you can actually download. And you can actually put it in Julia. And you can compute this solution in one line if you'd like. So you just go using the software package, that's the name of it. And you call psi was the original name for this, so bad software design choice, I guess, but okay. So you want to evaluate it at x equals 2, t equals 0.5, c1 equals 1, c2 equals 2i. And this 1 is a scaling, amplitude scaling parameter. You can always set it to be equal to 1. And you get the answer, okay? All right, so now I can talk about asymptotic properties. Okay, in the channels, what's happening? So I'm looking at this green region, and I'm sending xt to infinity in this green region. And that green region in these density plots coincides with the exterior of this hourglass-shaped white region, okay? Here it's a bit distorted because here C1 is 1/4. You see that these oscillations seem to connect, okay? But still the region exists, all right? So in that case, there's a controlling exponent in the Riemann-Hilbert problem. That's this Laurent polynomial. And it has real simple critical points, 3 of them, called Z1 to be and Z2 to be closest ones to the origin. Z1 is the -1, Z2 is the +1, all right? We then have the following theorem. Here's the large X behavior, okay, written as a large X asymptotics for this solution. So there are two quantities we need to define. First, the amplitude of C2 over C1, okay? That's called tau. And there's a related quantity P defined in terms of tau, all right? And then Q is given by, okay, 1 over x to the 3/4, that's the size of the leading term, times 2 exponentials, contributing from each critical points, all right? And the exponentials depend on x in pure phase, okay? So there are some fast oscillations here and slower stuff, okay? And the error is of size x to the -5/4, and this error is uniform as long as one stays away from the boundaries and tau stays under control both away from 0 and away from infinity. Okay? And everything is explicit. You can just go to Mathematica and plot this formula. Actually, we did plot it. Okay? So these curves are the real and imaginary parts of the asymptotic formula, and the dots are the solution computed with the Riemann-Hilbert problem solver. Right? So they are on top of each other, okay, to eyeball accuracy, but that's maybe not terribly convincing because it's an asymptotic result at the end, so it's all about the rate. So what we did was to take the difference of the leading term and the actual computed solution, and then do a log-log plot as x becomes large, okay, for a bunch of x values, all right, that increase, and then do a best fit line and look at the slope, and that's what comes out. So it's pretty close to -5/4, so the error is sharp. Okay, so this asymptotic result has a corollary, which is important enough to state as a theorem. So if you pick C1 and C2, this family of solutions, all of them, lie in L2 but not in L1, and they are L2 norm squared of 8 independently of C1 and C2. Okay, yeah, it was surprising. So how about the large time behavior? Okay, that's interesting, right? So that's the complement of the region that favors the complement of the previous region, which favors the time axis, okay? So then, of course, now there's a more complicated controlling exponent in the Riemann-Hilbert problem. This is called H, okay? If W, which is this ratio, all right? You can think of W as rescaled space because you are sending capital T to infinity, all right? Then it has, again, two critical points, Z1 and Z2, and also two branch points, okay? It's not an analytic function anymore. They are all explicitly given. The branch points are complex conjugates of each other. And then here's the large time behavior of this solution. Again, away from the boundaries, the error is uniform, and the leading order size is T to the -1/3. As you can see, the cluttered, let me put it, information coming from the critical points, they enter in the next term, subleading term, which is of size T to the -1/2, okay? Again, this error is sharp as long as W stays away from its critical value, which means that you are going to infinity away from the end boundaries, and this tau remains under control, okay? All right. Again, every quantity you see here that looks like a real positive amplitude, it is, okay? Every phase you see that should be a phase, it is a phase. It's just real functions, okay? So, all right. In the interest of time, I should skip. So you can actually give a complete description of this interference pattern in terms of by approximating the modulus squared, but I will skip because I'm running short in time. So I'm going to avoid a busy slide about the transitional asymptotics. The leading order term, when xt goes to infinity near this boundary curve of these two regions, is not that, is more transcendental, is the point. The solution is the leading order given by the unique increasing tree-trunc solution of the Painlev 2 equation, which is this non-homogeneous equation, where alpha, that non-homogeneous term, is 1/2 plus IP, where P is related to the problem we are solving. P is determined in terms of tau, which is determined in terms of C2 over C1. And this solution is determined from its asymptotic behavior. Alpha shows up in the subleading term, okay. All right, in this sector. All right. So what's next? So new directions and outlooks. So, okay. So here are some facts about the initial value problem. I have also some handwritten slides coming up about it. So far, what did we establish? We established the following, right? So we have a family of global real analytic solution of focusing analysis equation, okay, that are in L2, but not in L1, all right? So the Cauchy problem for the focusing analysis equation is globally well posed in L2, okay, that we know. And this solution decays at the rate to the negative 1/3. So this family of solutions do not generate any coherent structures like solitons, etc., for large time. Also, they don't exhibit the expected decay rate, t to the negative 1/2, right? Consistent with solitonless initial data in smaller spaces like H11. So here's the picture I have in mind. So in my mind, the white part is L2, okay? So we have L2 here, and there's a smaller, okay, weighted H1 space here, okay? F is in H1 and X times F is in L2, okay? And you pick a generic data here. What does it mean? Okay, there's an open dense subset of such data, but data that has finitely many simple eigenvalues for the Zakharov-Shabat problem. If you pick such data, as t goes to infinity, okay, one of the two things happen. If you have solitons on your initial data, okay, the solution does not decay, it just latches itself onto these solitons, okay? And there's, of course, some radiation that decays in subnorm proportional to t to the negative 1/2. Or maybe there are no solitons at all in your initial data and the whole thing just decays, again, of size, an infinity norm, t to the negative 1/2. This was proven by Borghese, Jenkins, and McLaughlin. It's the soliton resolution for the focusing analysis equation. Okay, so yellow things are the H11 generic data. That's the scenario. So it seems like these log waves of infinite order are on this line because actually up to a constant phase factor that depends on C1 and C2, they are actually really parameterized by a real parameter. So, okay, so you can work that out, all right? And they decay like t to the negative 1/3, all right? So doing neither of those, all right? So they are somewhere in between. But they're in L2, not in L1, so no IST for them, okay? At least in the out-of-the-box sense, all right? What I really want to know, that's the outlook part, is whether there's an L2 ball or maybe like a slit ball, okay? Maybe one direction you generate solitary waves if you perturb it, but whether there's an L2 ball around this line for which this anomalously slow time decay persists. Or maybe you lose it immediately if you perturb these solutions. So that's some ongoing work. Then another ongoing work, and we have been working on these aspects of it with theory for the past year or so. What causes this? Like, can one really identify some future, maybe try to go back to scattering data and back out information about it, all right? So, of course, because it's not in L1, you don't have the out-of-the-box scattering transform for this solution, okay? So there's no straightforward way to obtain quantities such as the reflection coefficient, the transmission coefficient, or the Yost solutions, all right? But maybe the potential behavior, singular behavior, of any of these quantities to the extent that they make sense, okay? I'm speculating, all right? That may shed light on what causes the slow temporal decay. Like, what's special about that 1/3 power, right? So, but how to interpret them though? Okay, so maybe something that can be done, and we have some work towards this direction currently, okay, is that we already have a Riemann-Hilbert problem, so we have access to the eigenfunctions, and the determinant is 1, so you have a fundamental solution of this equation actually away from lambda equals 0. So renormalize and maybe study the behavior of your solutions. That's one thing to understand. All right, and the other thing is really just coming from our discussions when I visited Rowan Killip, Monica Vishen, and theory back when he was at UCLA. From this paper, the reciprocal of the transmission coefficient in the scattering theory for this Zakharov-Shabbat problem actually extends to L2 potentials in the sense of a perturbation determinant, where I denote by matfrak A here. And it depends continuously to the potential in L2, all right? So, okay, so that motivated this theorem, which we recently proved with theory. So converges in a more useful topology depending on what you want to do, all right? So one can rescale the multisolitons, okay? These are our rescaled multisoliton potentials, and this is the profile of the Rogue wave at t equals 0. Okay, C1, C2 are arbitrary but non-zero. And the convergence actually goes through in L2. You can prove it. All right? So here are some pictures, again, of the dotted one is plotted, okay, on top of the finite order ones. And of course, then you can explicitly write down what the reciprocal of transmission coefficient goes by the A function in scattering theory. Okay, for the rescaled multisolitons, okay, it's just this Blaschke factor. And you just take the limit in L2, send k to infinity. You realize that, oh, okay, this extension of that transmission coefficient's reciprocal is e to the negative 4i over lambda. Okay, that's what comes out, right? But then this suggests the following. You know, for the usual A function, this agrees with the usual reciprocal of the transmission coefficients for Schwartz class potentials, right? And if you take the logarithm of it and do a Laurent series expansion at infinity, the coefficients give you the conserved quantities, all right? So this suggests that all the conserved quantities for this family of infinite order solution, they exist, it turns out, except for the L2 norm should be identically 0, because if you take the logarithm, I mean, this is not a proof yet, okay? We need to tie some loose ends, but if you take a logarithm, okay, the Laurent series expansion has just 1 over lambda. That's it, right? Nothing else. So all the rest is 0. And this reminds me of this morning's talk, by the way. It's very similar to the situation for algebraic solitons for the derivative analysis equation. There, you also only have the L2 norm. The rest is 0. Okay, so beyond NLS, okay, is this specific to focusing NLS equation? Not really. Okay, so you can consider, for example, the focusing AKNS hierarchy. So what do I mean by that? Okay, so let T to be this vector of times, tuple of times. There are n plus 1 of them. The X problem in the Lax pair is exactly the Zakharov-Shabbat problem. Psi now depends on X and a tuple of times, T. And then you can pick one of these, okay, any one of these, and there's a time equation with respect to that time, where the coefficient matrix is now a higher order polynomial of lambda. Okay, so one may choose the highest one to be negative I sigma 3, and all the rest of the coefficients are determined by this compatibility condition. Okay, it's a recursive business. All right, that's called the AKNS hierarchy. All right, so if you look at the outcoming equations, okay, forget about n equals 0. N equals 1 is the transport equation. Then you get focusing NLS equation. Then there's the focusing complex MKDV, so on and so forth. All right, so what you can do is you can just take this psi to be a simultaneous solution of all these flows, because why not? Okay, and then, okay, define such a solution for which you can take this high order limit, right? Okay, so it's like an analog of a soliton, multi-soliton solution that's simultaneous to the hierarchy. The Riemann-Hilbert problem looks almost exactly the same. All is different is that, oh, okay, there's some G matrix conjugated by these Blaschke factors to the power integer over 2. And K is the order. And the phases are no longer the NLS, they are these higher order polynomials, okay? And then, okay, you can prove that this Riemann-Hilbert problem has a unique solution, and its unique solution produces a solution of the focus simultaneously of the first n plus 1 equations in the flow, all right? Okay, and then the near field exists. You can take this limit, you can just go into each time axis and rescale it appropriately, and take a large order limit. and it will converge to a profile, limiting profile of capital X and a vector of capital T variables. And that object defines a simultaneous global solution of the first n+1 complex flows in the AKNS hierarchy. Okay? So it's a generalization of this infinite order solution simultaneously to first several but arbitrary flows of the hierarchy. Of course, if you zero out everything but t equals t2, index 2, then you get the NLS case. So I think I'm running out of time, but I'll give you 2 more slides to show you. First, you might ask, like, any common asymptotic behavior as xtn goes to infinity for general n. So pick one of the flows, give the same initial data, and see what happens. Okay, maybe you can tell generally for given n. The answer is yes. Actually, you can say a lot. It's work in progress, but that's a story for another day. Okay, I'll just give you the MKDV result to end the talk. So you can do the large X behavior. Again, it looks like x to the 3/4 times a cosine that depends on fast stuff, not so fast stuff, and just constant in x stuff. All right, as x goes to infinity, it's of size 3/4 and decays like 5/4. That's asymptotics in this region. And as you send t to infinity, asymptotics in this region, this capital G, the leading order term, it depends on theta functions. It's of size order 1. But it decays at a rate proportional to -1/4. All right? So again, you have very slow decay. And you know that this is a solution in L2, but not in L1. Okay? I'll end the talk with a small time evolution movie for the MKDV equation for this profile. So thank you.
Okay, there's a little bit of time for questions.
Really, I couldn't use it all up. Okay.
Try and keep it short. So when you drew the picture with what I would call the separatrix, your go-to was to say it's not a separatrix, there's a ball.
No, not the goal. I want to know if it is a separatrix or not. So maybe when you perturb, it's all gone. So then it's separatrix.
It's not a separatrix?
Sorry?
Do you have any evidence that it's not a separatrix?
No. I want to know. That's why I put out the idea whether there's a ball or some open set around it.
Contrary.
Yeah. Okay.
All right, so, but similarly,
Hopefully
do you
not.
have any reason to believe that half a soliton is not also in the separatrix?
Sorry?
Half a soliton.
What do you mean half a soliton?
Take the soliton, multiply it by a half, so it has a resonance, no eigenvalue.
Oh, I see. Okay.
Do you have any reason to doubt that that's also in the separatrix?
I don't know. I don't know. I don't know the time decay rate for it, actually. Yeah, okay. But maybe we can work it out. Yeah, okay. Interesting. Yeah.
Yes, I have a question about the large time behavior. So you showed us the t to the power 1/3, minus 1/3,
Yeah.
in comparison with minus 1/2. Can you say something about the phase? Because in the classical case, you would have a logarithmic phase. Do you know, can you say something in your case?
Yeah, so I don't remember on top of my head what this depends on, but it doesn't depend on t is the point.
So you don't see the log t as...
In the phase? No. The t dependence in the leading order term, this is the first line is the leading order term. And the only time dependence is multiplying this quantity that's independent of t, that's kappa, that's it. So it's pretty oscillatory, okay? It's not log of t, it's t to some power, okay? But there's no logarithm, and then there's some decaying profile here.
Any other questions? So, like this renormalized transmission coefficient that you said you can formally achieve it by this limiting of Blaschke factors, which is
that limit, I think, is not formal in the sense that because it depends continuously in L2.
Okay.
And I have convergence in L2.
Okay.
So So
Okay,
that's airtight.
okay. So that limit, if you take the logarithm, I might be wrong. I believe you get it as a Poisson extension of the Dirac delta or something like that.
Yeah, I don't know.
So my question would be like, it seems to me that like the transmission or maybe reflection, transmission coefficient of this potential is basically the Dirac delta centered at 0.
Yeah, there's something like that. I didn't put in the slides because it's ongoing work. Yeah, but you're right.
So
Yeah.
my question would be,
There's some
is there any
singular
way of
part. Yeah,
making
there's some
sense of
singular
this?
measure. Yeah, right.
Yeah.
Yeah. So your hunch is correct. Yeah.
Okay.
Okay, let's thank Deniz again for his talk.